Okay, so we're starting section 3.1 today. Chapter 3 is all about exponential functions, but then we also get into log functions as well. And it turns out that if you know your rules for exponents, neither of these things are difficult. What was your experience with exponential functions last year? Were you kind of like, yeah, no big deal? How about logs? Usually it's like, oh, exponentials aren't so bad, but I hate logs. Logs are so hard. But it's the same thing. Exponentials and logs are the exact same thing, just in reverse of each other. So logs kind of seem weird because of the notation. So usually that takes a little bit longer. My hope is that by the time we finish chapter 3, that you'll feel just as comfortable with logs as you do with exponentials. But both of those things rely on you knowing some pretty basic rules for exponential or exponents, which is the purpose of what we're reviewing here. So did you have for the first one here, anything to the 0 power is equal to 4? Did you know that? Except for 0 to the 0 power is undefined, but everything else is equal to 1 if it's an exponent of 0. For this second one, did you think to put a 1 on that 2 there? And you know the rule for what we do with those two exponents? We add them. So that should have been 2 to the x plus 1. If you didn't have that, make note of that. Which would make this one 2 to the x plus 5, right? Do you remember the shortcut? What we do when there's an exponent inside and outside of parentheses? Multiply the exponent. So this would be 2 to the 3x. Negative exponents. Things with negative exponents, sometimes we think about them moving to the bottom of a fraction or 1 over the value. So negative exponent of -1 means it goes on the bottom of a fraction. In general, a negative exponent means it ends up on the bottom of a fraction, but it's a positive on the bottom. What'd you get for this one? We already did this problem. It is the exact same as that, isn't it? Same thing, slightly different looking format. You are multiplying a 2 to the first times 2 to the x. That's 2 to the x plus 1 or 1 plus x, same thing. A lot of my students want to do on this last one, a lot of them want to cancel the 2's and say that it's equal to x, but we can't do that, can we? So if you think about this as 2 to the first, we could write this as 2 to the x minus 1. So you're going to be doing this type of work in a lot of your problems because they'll give you some weird looking exponential functions, and you'll have to kind of play around with the rules of exponents to make it look more familiar to you. So we should be feeling fairly confident with all of those. If there's something there that you're struggling with still, or you're not 100% sure, please let me know when we get a chance here, or schedule some time with me. I'd be happy to go over that with you. But my assumption is at this point that you all can simplify these like quick. Okay. And maybe you're a little bit rusty on it, but once we get going with this, we've done a couple homework assignments. We want to be really quick with these. All right, so you're not going to see problems like that in the homework, but you will see problems come up where you have to use that simplification as we go along. So again, let me know if I can help you in any way with that. Let's move on to our actual notes for today. We're going to start off with a basic exponential function. So we're getting into 3.1 here. So we're going to start off with a simpler case with just b to the x. We're eventually going to add an a in front of this to deal with our general case of an exponential function. But I just want to mess around a little bit and remind you what the graphs of these functions look like. We'll do a little bit of analysis as well, practice our chapter 1 skills. So let's start with a simple function, f of x equals 2 the x. We're going to make a little xy chart and plot a couple points. -0. What am I thinking? What I meant was -1. -1, 0, 1. Those are 3 most important points. I'm going to ask when we graph exponential functions that we graph at least those 3. I'm going to do a couple extras for this first example. Let's go ahead and do 2 and 3 also, but those won't be typical points that we'll do. So if this is x and this is y equals 2 to the x power, go ahead and find those values. What is 2 to the -1 power? 2 to the -1 would be 1 over 2. And 2 to the 0 is the same thing that anything to the 0 power is. 1. We plug in a 1 for x, we'd have 2 to the first, that's 2. 2 to the second, it's 4. 2 to the third is not 6. 2 to the third is 8. Why not? Just for fun, let's do -2 also. What's 2 to the -2nd? It'd be the same as 1 over 2 to the second. So 1 over 2 squared is 1/4. All right, let's graph this bad boy. Oh, that's bothering me. That's better. All right, what do we got? -1, comma 1/2. -2, comma 1/4. 0, 1, 1, 2, 2, 4, 3, 8. And let's sketch this thing. And my hope is that this is looking pretty familiar. Did you graph a whole bunch of these last year in Algebra 2? Maybe some of them, probably. It's been so long, it's hard to remember. We're going to be graphing a bunch of them here. But that's that typical shape you see for an exponential. An exponential, typically on one end, it's going to be really close to 0. Sometimes we'll shift it up or down. And the other end, it's going to be growing really fast, exponentially, in fact. Let's do our super fun analysis thing that we did from chapter 1 and just practice with that. So for this particular function, 2 to the x, domain is all real numbers. We can put anything we want into an exponent. What about range? 0 to infinity. Now, does an exponential function ever get down to 0? It gets really, really close, but it never actually hits 0. So 0 to infinity, but not including 0. Parentheses for that 0. We could also say y is greater than 0. Strictly greater than, not greater than or equal to. Increasing, decreasing, constant? It's increasing. Always increasing, right? It's increasing for all real numbers. Negative infinity to infinity. Continuous? Yeah. Yes. What else do we talk about? Continuity, symmetry? Any symmetry? No symmetry. We talked about boundedness. Are we bounded below, but not above? Any local minima or maxima? No, because it's increasing for its whole range, for its whole domain. We can't have local mins or maxes. Because a min or a max means it's going to change from increasing to decreasing. So no mins, no max. That'd be another good way to say it. No local extrema. Any intercepts? It's got a y-intercept at 0, 1, but no x-intercepts because it never hits the x-axis. We'll do, we'll do our limit notation. Before we do that, asymptotes, any asymptotes? There is a horizontal asymptote at y equals 0. So there is a horizontal asymptote. I should probably sketch that in here. Dashed line along the x-axis. And then, yes, thank you for reminding me about end behavior. Let's practice using our limit notation for end behavior. So we'll talk about when x goes to the left, negative infinity, and when x goes to the right, positive infinity. So what is our y value doing as we go way off to the left of this graph? It levels out and it heads towards 0. It never actually hits it, but that's okay. We can put it 0 there because that's kind of what a limit means. We'll learn lots more about that next year in calc. And as we go up to the right, what's happening to our y values as we go up to the right? We're going up and up and up and up and up, heading towards positive infinity. All right. I want to make a small change to this and discuss what would change in terms of our analysis. So let's look at another function. What if I changed, instead of 2 to the x, what if I changed it to 0.5 to the x? What's going to change here in our table? What's going to change in our analysis? Anybody know what 0.5 to the negative 1 is? 2. All right. It'd be 1 over 0.5. 1 over 1/2 would be 2. Yes, it is 2. 0.5 to the 0 power is the same thing that anything to the 0 power is. That's 1. Anything to the first power stays the same, so that would be 0.5. 0.5 squared is 0.25. 0.5 times 0.5 is, yeah, is a quarter. That should be enough for us to get a rough idea of what this thing looks like. I don't have any negative y's here again. My hope is that that looks familiar to you also. That's another typical shape for exponential functions. So let's highlight the things that have changed in terms of our analysis. Domain's still all real numbers. That didn't change. The range didn't change. I'm still going from 0 to infinity. It's not increasing anymore, though. It'd be decreasing. I'm just going to put a star next to this and underline it. That could change. Still continuous. Still no symmetry. Still bounded below. That's true. No min and max is true. Is our y-intercept still at 0, 1? Yep. Horizontal asymptote in the same place. End behavior would be swapped basically, right? So that would be different as well. So our analysis stays the same for everything, but potentially increasing, decreasing, and end behavior could change. So we'll talk about exponential growth versus exponential decay. Does anybody know the key thing when you're looking at an equation? How can you tell whether it's going to be growth or decay? Yeah, not the coefficient. We're going to end up calling this something else. B stands for base. We'll end up calling this the base. Yeah, you can look at the base to tell whether it's growth or decay. And we're going to put this in our notes in a minute, but kind of a preview of that. What's the key thing? How do you know if it's going to be growth versus decay? Say again. If it's less than 1, it's going to be decay. If it's greater than 1, it's going to be growth. And if it's equal to 1, it's not really an exponential function. It would just stay the same. It would be a flat line. Yeah, so greater than 1 versus less than 1. So if you saw an exponential equation where it was like 1.1 here, that's still growth. 0.9 though would be decay. Hey, I got some great news for you. There's a whole section of your homework where all you have to do is look at the equation and say whether it's growth or decay. Where is it? I just saw it a second ago. Yeah. So you'll look at something like this to determine if it's growth or decay. So I'm looking at this one right here, C32, how it's 1 over E is the base. 1 over E, that's, you know what E is. It's like, well, pi is 3.14, kind of. E is about what? Does anybody know what E is? 2.7-ish? Yeah. But if I do 1 over that, that's definitely going to be less than 1, right? So 28, or sorry, 32. The answer is decay. Spoiler alert. So there's some of these. Now, some of these you're going to have to like, this one, 3 to the negative 2x. You would need to turn that into something that looked like something to the x power. So that's where you'd want to fall back on your exponent rules that we did there. So I'll just show you what that'll look like. They say 3 to the negative 2x. You would need to rewrite that as 3 to the negative 2 to the x. And what is 3 to the negative 2? 1/9 to the x. That's really what you're looking at there, which is definitely decay because 1/9 is less than 1. This is why I said you need to know these things, because you need to be able to look at this and say, that's not in a form I want. I can really quickly turn it into 1 over 9 to the x. You need to know those exponents. Okay. Offer still stands. If you're struggling with the basic exponent rules, come see me and we'll get you fixed up. All right. Let's move along here. So we did our analysis from chapter 1. What else should we practice from chapter 1? Oh, I know. Let's do transformations. You guys love transformations, right? We saw those on our tests. You guys should be feeling very confident about transformations at this point. So we're going to do a little bit of analysis with transformations. So we're going to graph using transformations. You'll want graph paper for this. So if you've got some, hopefully you've got some with you. If not, I have some graph paper in that pile over on that bookshelf. All right, I'm going to show you, I'm going to walk you through this. And while I'm doing this, I'm also modeling what I expect to see on your homework. Okay, so my first example, we're going to graph the function f of x equals 4 to the x minus 2. Yeah, both of these are part of the exponent. So we're going to do these kind of like we did back in chapter 1. I'm going to ask you to make some tables and tabulate the points, and then we'll graph our final after we've done that. So we're going to start off with our original parent function, which would be y equals, and we want it to be one of those basic functions. And I can tell by looking at this that my base is going to be 4. So I'm going to start with the table for y equals 4 to the x power. And we're going to tabulate some points for that. So x and y. And I got great news for you here. You'll be happy to hear this. There are only 3 points that I need you to do when you're graphing these. X value is, starting x value is negative 1, 0. So plugging negative 1 in here, 4 to the negative 1 is 1 over 4. 4 to the 0 is 1. 4 to the first is 4. And we got our 3 points. Now on the homework, I don't need you to graph every step along the way, but I think for our notes, it's a good idea to do this. So I'm going to graph the original. And I'm going to make this dash because this is our, so it's not our final graph. All right, I want you to use your chapter 1 skills of identifying transformations and tell me if I pull this x out and I replace it with an x minus 2, what is that going to do to my graph? Is it going to stretch it or shrink it? Is it going to shift it? Is it going to flip it? When we pull the x out on the inside and replace it with x minus 2, I'm seeing people moving things with their hands. So shift. Which direction? To the right. Okay, so this is happening inside of the function. Right? If it had been minus 2, like after the function, that would be outside, but this is happening inside of the function to the x, and it's minus 2. We know things that happen on the inside are kind of backwards, so minus 2 is going to move it to the right. Now, in terms of, well, let's write this down. So shift right by 2. So I want you to write out in words what are going on, and then write down your new x and y coordinates. Now, if I'm shifting to the right, only one of these columns is going to change. Which one is it? Is it the x column or the y column that are going to change? The y's are going to change because we're shifting up and down. The x's are going to change because we're shifting to the right. The x's are different, but the y's stay the same. Go for it. I saw your name on the thing. Congratulations. Another trip around the sun. Can we all sing? No. We'll sing later. All right, here we go. What's going to happen to my x's? If I'm shifting something to the right by 2, then my x coordinates are going to grow, aren't they? Are they going to get bigger if I'm moving to the right? Bigger by 2. So I'm just going to do basically plus 2 to each of my x coordinates. So negative 1's going to become positive 1, 0 is going to become 2, 1's going to become 3. And now I can plot these new points, and that should give me my final graph. So 1, 1/4, 2, 1, and 3, 4. And there's our graph. Missed it. And we can see visually that we have managed to shift our graph to the right by 2. All right, any questions on that one? We're going to have 2 more of these. Any questions before we move on to the next? All right, here we go. Next example, this time f of x equals 3 to the 2 minus x. Okay. I tell you that things get a little tricky in this unit. Remember back in chapter 1 when we were dealing with transformations, and we kind of briefly touched on how the order of the transformations makes a difference. And I said we don't have to worry about that too much in chapter 1, but it will come up later on. Well, here we are. It's later on now. And the order of transformations makes a difference. Okay. So there's a couple different ways you can do this. I'm going to go with like one simple rule that has no exceptions, because that's the easiest way for me to deal with stuff. So here's my thing with transformations, and this will work 100% of the time if you can get it into this format. So if you can get anything on the inside, so I'm going to write a little note off to the side here. This is just in general. If you want your inside of your function to look like something times x plus or minus something like this, okay? You don't want a coefficient in front of the x. You want the x to be by itself inside of a set of parentheses. And if there's a negative or if there's a coefficient or something on the x, you want that to be outside of the parentheses. And then on the inside of the parentheses, just your x plus or minus something. If you can get it into this form, then you can know that 100% of the time that your shifts happen last. If you don't have it in this form, then the shifts might need to happen before you take care of any reflections or stretches, or maybe after, and it's kind of hard to tell. Okay, but if you get it into this format, then you can be sure that the shifts are going to happen last. So anytime I see something that has multiple stuff on the inside of the function, I want to try and put it in this form. So I'm going to play around with this function a little bit before I start graphing it. 3 to the 2 minus x is the same as 3 to the negative x plus 2. That would be my first move right there. But you see how that's still not quite in the right format? I don't want this negative attached to the x. I want there to be a parenthesis there, and I can't just throw a parenthesis in here. In order to make that happen, to get this, I'm going to have to factor that negative out. That's how the negative x is going to turn into a positive x. But what's going to happen to the plus 2? It's going to become a minus 2. And now this matches that format. And so I know that I'm going to eventually do, it looks like this one's also going to have a shift to the right by 2, but that's going to happen after I do this other transformation. And what's the negative going to do? Reflect it over the x-axis or the y-axis? It's on the inside. The negative on the inside should reflect it over the y-axis. It should be moving it horizontally, right? Inside is horizontal stuff. And if I'm moving a point horizontally, it's going to end up flipping over the y-axis. All right, so let's do our tabulation. We're going to need 3 tables this time because we have 2 different transformations. Our starting table, we're going to start out with y equals just 3 to the x power. I should have left myself a little bit more room, but that's okay. And then again, the only points that we need to worry about are -1, 0, 1. And our y coordinates should be pretty simple. Oops, that's a 1, not a 0. Rookie mistake. I'll go ahead and graph this as we go off to the side here. I'll just do this in as dashed. So that's my original function. Since we put it into this format, we have to save the shifts for last. So we've got to take care of the minus first. So we said that was going to be a reflection over the y-axis. Over y-axis. So y equals 3 to the negative x. So we're dealing with that negative on there first. And then we'll come back and deal with the x minus 2 at the end. Since this is happening on the inside of my function, it should only affect my x coordinates, right? Inside is horizontal. So just x coordinates are going to change. My y coordinates should stay exactly the same. So I'm just going to copy my y coordinates down again because they're not changing. My x coordinates are all going to change. And when I do a reflection, it just flips the sign on them. So a -1 becomes a +1, +1 becomes a -1, and 0 stays 0. So we're just doing a sign flip. So that point didn't change, that one did. And then one more transformation to get us there. Oops, I forgot my base on there. 3. When I take that x out and I replace that x by x minus 2, that's going to be a shift. Which direction? X minus 2. Shift right by 2. Should it be, I'm sorry. Was there a question? Mm-hmm. It is in this format. I would need to do the shift left first, and then a reflection afterwards. So there's a lot of rules about what comes first depending on what form it's in. What I'm going to encourage you to do, and there's a couple of reasons for this. One, I think it's the simplest. If you can get the inside into this format, I think it's the simplest because then you know automatically your shifts are last. The other reason I'm encouraging you to get it into this format is when we get into chapter 4, which is graphing trigonometric functions, you definitely want it in this format. So if we get used to that right now, then when we get to chapter 4, you'll kind of already be in that mode. Does that make sense? So I'm going to encourage you that anytime you see an x that has a coefficient on it, try and factor that coefficient out. And factor it out of everything. We didn't just factor it out of the x here. We factored out of both the x and the +2 on it to get it into this format where it's x plus or minus something on the inside, and then any coefficient, including a negative, ends up on the outside of your parenthesis. Then you won't have to worry about whether the shift comes first or last because the shift will always come last if you do it in that order. All right, if I'm shifting right by 2, then my x coordinates should be changing again. My y coordinates should stay the same. When shifting to the right by 2 is just going to increase all of these by 2. So I'm just going to do +2 to each of my x coordinates. So we get 3, 2, 1. And the y coordinates did not change. Still 1/3, 1/3. We'll graph our final version here, make it solid line. So 3, 1/3, 2, 1, 3. This is going to be my final function. So the question came up a minute ago. Gabby was asking, doesn't this show a shift to the left instead of a shift to the right, this +2 here? And the answer is yes, except if it's in this format, we would need to do the shift first because we still have something attached to the x, and then whatever is attached to the x last. So if you thought about it, if I took my original one and I shifted it to the left by 2, this point would have ended up here, right? But then after I reflected it over the y-axis, it would end up at that spot. So we'd end up with the same graph either way. It's just that I'm always going to work to get it in this format because I'm used to it. Because this is how we've seen most of our work with transformations before. And that's how we're going to be dealing with trig functions later on as well. All right, I got one more that I'd like you to do. We haven't done much in the way of vertical transformations, so we should probably pick one that's got some vertical stuff going on. And we'll work together on this. We're going to do negative e to the 2x plus 3. Oh, this should be fun. You might need your calculator for this. You're not super confident with e. I get you guys to look at your calculator. See if you can find the E button on your calculator, first of all. It's pretty close to the pi button because it's another one of our big important constants. Do you see where E is on your calculator? It's on the right side. It's the divide key. Well, there's actually a couple places. There's an e to the x over here, and then there's just an e over here if you want the e that's the constant. Go ahead and type e in and hit enter and let your calculator remind you of the decimal value for e. E is one of those irrational numbers. It's real, but the decimals do not repeat any kind of pattern. Super important number. Comes up in a ton of applications. And it is tied to, well, it's tied to exponential functions. It does kind of look like they're repeating, but they're not. If you were to keep going, they would. There's no pattern to it. But yeah, I see that 182 kind of happening. 1828, 1828, yeah. All right, so let's talk through our transformations here before we get too into this. You know what? I'm sorry. I'm going to change this on you. I'm so sorry. I meant for this +3 to be on the outside. All right, let's start with the +3. What's the +3 going to do? It's going to move it up because it's on the outside. We're going to do that last, okay? This is kind of in that format that we talked about a second ago, so this is going to be last. How about the negative that's happening to the whole function? That's going to be a reflection over the x or over the y. This is a vertical move because it's on the outside. And if I'm moving things up and down and reflecting, I'm going to be reflecting over the x-axis. And this 2 is multiplying by the x on the inside of the function. On the inside, everything's backwards. You would think multiplying by 2 would make it bigger, but this is going to actually shrink it or contract it by a factor of 1/2. So it's going to make things smaller. Horizontal shrink by a factor of 1/2. All right, so let's start off with y equals e to the x. We'll do our little table. -1, 0, 1. And I'm just going to write some decimals down here. My ultimate goal here is to graph this thing. So I'm going into my calculator and I'm doing e to the -1, just to give myself an idea of what that is. E to the -1 is about 0.37. I'm just going to say about 0.4. That's going to get us close enough. E to the 0 is 1, and e to the first is about 2.7. So we got options for how we tackle this. We want to do our shift last. So do you want to do the reflection next or the horizontal compression next? Horizontal compression it is. So we're going to horizontal compress. Our book says shrink, so I'm going to be consistent with them. Horizontal shrink by not 2, but 1/2, by the reciprocal of 2. And that's going to get us y equals e to the 2x. And is a horizontal move going to affect my x coordinates or my y coordinates? X coordinates, and they should all end up half as big as they were originally. So each of my x coordinates is going to be multiplied times 1/2. So instead of -1, I got -1/2. 0 times 1/2 is still 0. 1 times 1/2 is 1/2. Y coordinates remain the same. Let's just keep graph. Let's do this like we would do a homework problem. I'm not going to graph until we get to the last step. We're saving our shift for the end, so we got to do our reflection next. So we're going to reflect over, did we say the x or the y? We said the x axis. That's going to give me y equals negative 2x. So the negative, the question was why is it over the x and not the y? The negative is happening on the outside of the function. On the outside of the function causes things to move vertically. So if you think about a point in the first quadrant, if I'm going to move that point vertically and reflect, it must be reflecting over the x-axis. Does that make sense? That's kind of my link. I link things on the outside of vertically, and that helps me think. So if you've ever seen me kind of thinking through one of these problems, you'll see I'll be like moving my hand horizontally or vertically. Is that over the x or the y? That's over the x. That's my cheat code for that. And because it's a vertical move, it should only be affecting the y coordinates, correct? Our y coordinates should be changed. X coordinates should remain exactly the same. I'll go ahead and copy those over. But the y coordinates we're reflecting, so we're just going to do a sign flip. So they used to all be positive. They're all going to be negative now. And one more is going to get us there. All we got to do is tack that +3 on the end. And doing that's going to cause us a shift. We just did that. That was our reflection over the x-axis. Yep. So +3 is going to cause us to shift. It's happening outside, so it's either up or down. Outsides is as you would expect. +3 would cause us to move up by 3. So we're moving up by 3. Our y coordinates should be changing. Our x coordinates should stay the same. So I'll go ahead and copy my x coordinates down because those aren't changing at all. And my y coordinates should change. If I'm going up by 3, we're going to be adding 3 to each of the y coordinates. So negative 0.4 plus 3 would be about 2.6. Negative 1 plus 3 is positive 2. Negative 2.7 plus 3 would be about 0.3-ish. And that should be enough information for us to make a sketch. Oh man, I can't draw straight lines. All right. Negative 1/2, 2.6-ish. 0.2, half, 0.3. All right, I'm a little unsure how to make that thing look. So I'm going to come back and do one more thing. This is a true mistake. Sometimes we do that, right? Sometimes we throw a little extra mistake in there and say, oh, we should have done this. All right, but this is a true mistake. I'm not 100% sure what this is going to look like, so I'm going to do one more thing. Can I get you guys to backtrack with me? Eyes up here real quick. Let's graph also, in addition to these 3 points, let's also talk about the asymptote. The asymptote for this function would be the same as the asymptote for any function in this format, which we did at the very beginning. And the asymptote was y equals 0, right? Horizontal asymptote, y equals 0. Okay. Now think about this. If I reflect over, if I shrink horizontally by 1/2, Is the line y equals 0 going to change at all? No, it would still be y equals 0. Okay, two reasons. You can't shrink a horizontal line by half because it goes forever and ever in both directions, right? Not horizontally anyways. Also because it was the x's that we're changing here, and this is a y equals equation. So y equals equation shouldn't change with the x's. All right, now in our next move, we did change the y's and we did a sign flip. If I do a sign flip on y equals 0, what am I going to get? Sign flip 0 is still 0. And in our final move, we took all of our y coordinates, our y values, and added 3 to them. Now this time, it is going to change. We need to take that 0 and add 3 to it. It's going to become y equals 3. So we do have a horizontal asymptote here still, and it's at y equals 3. And when I draw that horizontal asymptote in, it makes it a lot easier for me to see what my final graph is going to look like. It's going to look something like that. All right, folks, how are we feeling? All right, so all this is kind of background right now. My hope is that we're starting to kind of brush off the cobwebs on our exponent rules and that we're feeling pretty comfortable with graphing some basic exponential type functions by starting with our basic exponential function and just graphing 2 points. So, all right, let's go on to kind of the key notes for today, which is our notes on the general exponential function. So we've been dealing with kind of the more basic exponential function. We're going to deal with the more general exponential function now. Before we just had f of x equals b to the x. We're going to do the same thing, but we'll throw a coefficient in front of it. This a value here, this is, it's a coefficient. I'm going to refer to it a lot of times as the initial value. It is going to be the value where the y-intercept happens. So if that number in front was a 5, then you would know for a fact that your y-intercept is going to be at 0,5. And we do not allow for exponential functions. We do not allow a to equal 0. You can probably convince yourself that a was equal to 0. This would be a pretty boring function, isn't it? Just be a horizontal. It'd be the x-axis, basically. There's no fun in that, so we don't want that happen. B is what we call the base. Some rules for the base is that the base has to be greater than 0. We don't deal with negative bases because weird stuff happens when we start dealing with negative bases. And also because it would just be way too boring, we don't allow b to equal 1. Because if b is 1, then you're basically multiplying a times 1 and you got another horizontal line. Now, there's kind of two things that can happen. If b is greater than 1, we're talking about growth. you're going to see a graph that's going to look something like that. If b is less than 1 but still greater than 0, we call that decay. All right. So that's our basic notes on exponential functions. We kind of graph some with some coefficients out in front. Keep in mind, if a ends up being negative, it is going to flip the graph over. So it's possible for something that's decaying to be increasing. Does that make sense? Let's look at an example of this. So if I had something like y equals -2 times 2 to the x, first off, I know exactly where my y-intercept is going to be based off of this. My y-intercept is at -2. And I know because my b value is greater than 1 that this is growth. But it's growth away from 0 because the graph would actually look something like this. It's a decreasing graph, but we would call it exponential growth still. Because it's not decaying towards 0. Basically, it's a matter of, is it growing away from 0 or is it decaying towards 0? And we would say that is growing away from 0. In the negative direction, but it is growing away from 0. Let's do one fun problem. I think it's fun. Real life numbers here. This is about the city of Ferndale. Anybody know what the population of Ferndale is, roughly? Yeah, good for you. So I looked up some census data. So in 2010, the population of Ferndale was 11,415, based on the 2010 U.S. Census. And in 2020, because they do it every 10 years, the population was 15,623. If you went onto Google right now and asked for the population, they're going to give you something bigger than that number. But it's not an official number because it wasn't an official census count. We won't have another one of those until 2030. We are going to assume exponential growth here, because that's a lot of times how cities and towns grow. So assume exponential growth. We're going to see if we can model the population of Ferndale as an exponential function. We're going to be doing a lot. This is much more 3.2 than 3.1, but it gives us an opportunity to kind of practice with that equation that we just did. So let's do it. Okay. So what do we know? I'm going to make myself a little XY chart here. And I'm gonna say let's make 2010 like our starting point. Let's have that be where x is 0. So we had 11,415 people. We're calling 2010 year 0. Probably a good idea for me to mark that. 2010. Some of you were probably born in 2010. No, I guess I'd be 12 years, 12, 13-year-old. That's possible. you have freshmen and pre-cal? 13 freshmen or they're 13-year-old freshmen. Okay. Okay, never mind then. Whew, okay. 2011, 2012, some of you were probably more. Anyways, okay. And that would make year 10, right? 2020 would be year 10. We're at 15,623. So if my goal is to write an equation to model the population so that we can predict what it's going to be in the future, the nice thing is these exponential equations only have 2 numbers in them. All I got to do is come up with 2 numbers to go on those 2 spots, and that's going to be my equation. And one of those numbers is going to come out of, let's say it again. One of them is going to come out of year 0, right? Because one of those numbers is our y-intercept, and I can see from my table that my y-intercept is going to be 11,415. Where's that go? Is that the first one? Is that the initial value or the base? Well, that's the initial value. That's the starting value, right? So 11,415 is going to go right there. That's great. And then all I'm missing is a base. How are we ever going to find that? I got an idea because we've done this in some other problems. What if I left it just as a variable for right now, and I found an x and a y value that I could plug in for x and y, and then I could solve for b? What do you think about that? Does that sound familiar? We did that with polynomials. We did it with rational functions. We're going to do it in this unit too. What x and y value could I possibly use that we could plug in for x and y? Oh, I know. How about those ones, right? Yeah, x was 10 and y was 15,623. We should be able to solve that equation. And before we do though, somebody make a prediction about b. Is it going to be bigger than 1 or less than 1? Bigger than 1, and you know that for a fact because that too. And also we are growing, right? We are getting bigger. So b should be greater than 1, right? If b is greater than 1, then we're dealing with growth, and we are definitely growing. So, all right, so we're going to divide this. Now, don't reach for your calculators just yet, okay? We're going to solve this, but we're not going to use the calculator until the very last step. I need you guys to hear this, okay? Starting in this unit, when we solve stuff like this, we do not use the calculator till the very last step. You're going to end up with huge rounding errors if you don't listen to this, okay? So I am going to start by dividing by 11,415 on both sides. And I normally wouldn't show that step, but I am because it's in my notes. My next step, which I would write down if I were doing a homework problem or a test problem, is this. And some of you are going to be like, why would you bother writing down that big nasty fraction when you could plug it in your calculator and turn it into a decimal? The reason is every time you change something into a decimal and you round something off, you're introducing errors into your answer. And when it comes to exponential functions, small errors in the middle of the problem become huge errors at the end of a problem. Okay, so we are not going to round until we type it into the calculator. Probably. All right, so how do we get rid of an exponent? We do a root. We're going to do a 10th root on both sides. And this is where I'm going to type it into my calculator. When I type, I'll just go ahead and type that whole thing all at once into my calculator. Do you guys know how to do a 10th root in your calculator? In mine, it is under math. I hit the math button and I use the one that has an X and a square root, but I actually have to type the 10 in first. So I type in the 10, I go math, X radical. That's going to give me a 10th root. And then since I'm putting a fraction in, I need parentheses to hold that fraction together. 15,625 divided by, oh, thank you. That would have caused errors as well. 11,415 in parentheses. I'm looking for something bigger than 1. All right. And I'd say for this, you're going to want to save at least 4 decimal places. When you're solving for B in a problem, in a word problem like this, you want to save at least 4 decimal places. In fact, I'm going to do even better than that. Let me show you something else here real quick. You got a bit of time. Rather than write, I am going to write it down, but I'm also going to stow that number. Do you guys remember how to stow a number? There's a stow button right above your on button. If you type that down, you're going to get answer and then a little arrow. And I'm going to stow that into B. And that's going to cause my calculator to not only save those 9 decimal places, but I think your calculator actually saved 16 or 32 decimal places. You can only see the first 9. But it's got it. It's in its memory banks. It's even more precise than that. And then when I go on to do anything else, I'm just going to use B. So for right now, I know that my function is roughly 11,415 times 1.0319 to the x power. So if I wanted to predict how many people are going to be here in what year? 2030. That's coming up not too far. 2030 would be year 20. I could just type this equation into my calculator and put a 20 in for x here. And I'm going to do that right now. But I'm going to use that stowed value for B instead of this rounded off value. So, sorry, trying to get it all on the screen at once here. So 11,415 times, and I'm using B to the 20th power because I've already stowed a much more precise version of 1.0319 in place of B. And according to our model, we should be looking at about 21,000 people here. That's only in like 4 years. No, that's only in like 7 years. 4 years. I get a little ahead of myself. 7 years. And then if you want to start thinking like really long term, like 2050, that would be 40 years afterwards. 2050, we're going to be pushing. I mean, we're going to be getting up there. That's 40,000 people. That's a lot bigger. Imagine Ferndale being 3 times as big as it is right now. And it's going to happen. It's going to happen. Now, is it going to grow quite like that? We're going to learn about this other thing called a logistic function in our next class. And what you'll learn is the logistic functions are better for modeling population growth. Just as a heads up, you are going to be doing 4 problems in your homework, 41 to 44, where they ask you to use a grapher to graph the function, find the y-intercept and the horizontal asymptotes. For these problems, I want you to sketch the graph. Okay, sketch. Remember what I meant by sketch. It doesn't have to be accurate. It needs to kind of have the right shape. And then find your y-intercept and your horizontal asymptotes. All of these graphs, spoiler alert, are going to look something like this. These are called logistic functions, and they're all going to kind of have an S-shaped curve. There's going to be a horizontal asymptote up here and another one down here. So just eyeball it and try and guess where those horizontal asymptotes are for these. That's 41 through 44. Your assignment is, and I'll get this on Canvas, it's not up there just yet. Oh, you only have to do it for a couple too. Sorry, page 286. We're going to skip 49. Yeah, you know what? Let's cross off 55 also. Sorry, I'm taking all these problems away from your assignment. I feel like I'm cheating you guys out of good math problems. You'll forgive me, won't you? I appreciate it. All right, thanks, folks. Let me know if you have questions.